Hello everyone, very good afternoon to all of you. Again, warm welcome back to Multimedia Studio, LNT College Muzaffarpur. In this video lecture, we are trying to continue the previous lecture. So that is actually the importance and significance of the Arrhenius equations and what are the catalysts and how the catalysis progress its role in a particular kind of reactions, right? So now we start from the Arrhenius equations. As in the previous lectures you have studies about the Arrhenius equation. So that is actually the rate constant depends on the temperature. So it is rate constant A exponential minus E upon RT. So nothing to explain about these terms. So as you know, all of you, as the rate constant depends on the temperature, it means if you increase the temperature, then the rate constant of a particular kind of reaction increases, and hence rate, right, with temperature this increases exponentially, right? So if you increase the temperature of a reaction, the rate of this particular or any particular kind of reactions will follow such type of exponential increased graph, right? So what happens here, once the catalyst is present in a particular kind of chemical reactions, its role is to minimize the energy of activation, right, so that it can attain a different and alternative pathway of minimum energy, and that will be responsible to effective collisions between molecules or reacting molecules, and then it can convert it back into products, right? So what happens here, we have a various type of reactions actually, and based on the nature of the catalyst. So homogeneous catalysis means here we are trying to add a homogeneous catalyst in a particular kind of reactions, right? So homogeneous catalysis means a catalysis where the phase of the reactant molecules and the phase of the catalyst are same, either solid, liquid or gas. So same phase of the reactants and catalyst will produce the product. So here we have actually adopted or reactions. So that is hydrolysis of sugar solutions. So that is C12H22O11 in a liquid form plus H2O in a liquid form, and in the above of the arrow we have H2SO4 liquid, right? So all the reactants here, that is water in a liquid state, and this particular sugar solution is also in liquid state, but this H2SO4 is also in liquid state. So you can simply say all these reactants and this particular kind of sulfuric acid, so that are same in phase, they are all in liquid state. So here this kind of catalyst actually is used to speed up or to enhance the rate of hydrolysis of this particular kind of reactions to produce glucose solutions and fructose solution in a liquid state. So such type of examples actually, they are homogeneous catalysis, and the catalyst used in this process are homogeneous catalyst. And another kind of catalysis, that is heterogeneous catalysis, right? So heterogeneous, as its name indicates that, so there will be a different phase of the reactants as well as of the catalyst. So both reactants and catalysts will be in different phase, right? So and the reaction progress take place and the product formed in this process. So suppose here we have taken example, the synthesis of ammonia through a Haber process. So that is actually nitrogen gas 1 mole and 3 mole of hydrogen gas. So both reactants are present in the gaseous form. So they react to each other to yield ammonia gas. So this particular kind of reaction actually requires a catalyst. So that is iron. That is iron in a solid form. So here iron is act as a solid catalyst and these are gaseous reactants. So gaseous reactants and solid catalyst, so both are in a different phase. So you can simply say that, so this is the a very good example of heterogeneous catalysis, right? And also that is one most important example, that is hydrogenation of olefins or alkenes. So in the presence of nickel, so you can simply say that is if there is a double bond CH2 that is ethylene, so that will react hydrogen gas. So this is also ethylene in gaseous state. So in the presence of nickel in the solid, so this double bond will be broken down and new bond will be formed on both carbon. So then this will CH3 that is ethane in gaseous form. So here the reactants molecule and products both are in the gaseous phase, but the catalyst here used, that is nickel, which is present in the solid form. So here is different phase. So that is why the phenomena of catalysis is actually called heterogeneous catalysis, right? So this is the beauty of, and overall what is the beautiful role of this any kind of particular catalyst is to reduce the activation energy so that reactants molecule can adopt different alternative pathway of minimum energy and convert it back into the products. So these are the examples of a catalyst and catalysis. Now one another kind of catalysis, that is positive catalysis. As you know that it has a name, positive catalysis. It means the positive impact of the catalyst. So catalyst can be used to enhance or increase the rate of a particular kind of reactions, so that we can get desired product in a major amount. So this is the positive catalysis. And here a very good example that I have taken from the reference, that is the conversion of the sulfur dioxide into the sulfur trioxide. Here simply this is the oxidation reactions. Once 2 mole sulfur dioxide in a gaseous state will react with oxygen gas, then it forms 2 mole of sulfur trioxide gas. So here the catalyst, that is vanadium oxides, so that is pentoxides actually, V2O5 in a solids, or you can simply use here are platinum solids, right? So this is actually vanadium pentoxides or platinum solids here used as a positive catalyst. So in the presence of this particular kind of catalyst, actually the rate of reactions have been observed as increasing, right? So now another kind of actually catalysis, that is negative catalysis, which will proceeds under the influence of negative catalyst, right? So negative catalyst here we have actually adopted a example. So that is sodium sulfite, that is 2 mole of 2Na2SO3 in the solid state, right? So here that will react with oxygen gas. Here solid react with oxygen gas in the presence of alcohol, that is liquid state. So it forms sodium sulfate, that is Na2SO4 in the solid state. So here 3 phases are actually present in this particular kind of reactions, that is solid, gas and liquid, and the product is solid. So what actually have been experimentally determined that, so in the presence of this alcohol solutions, right, in a this reaction medium, the rate of this reactions was supposed to be decreased, right. So and hence it will retards the rate of the reactions, so that it can form products Na2SO4. So in this kind of reactions, actually this alcohol will play as a negative catalyst, right. So here it has a role as a negative catalyst, right. And next example of the catalyst is autocatalysis, right. So autocatalysis means here in the reaction medium, so there is too many reactants are actually present in the reaction medium, but any one of them may act as a autocatalyst. So that is actually autocatalysis. It means this is 5 mole oxalic acid 5H2C2O4 and will react with 2 mole of potassium permanganate, that is 2KMnO4 plus 3H2SO4 in the acidic medium. So what happens here? It forms manganese sulfate plus potassium sulfate, both are the salts, and it will release carbon dioxide gas and it will produce water in the liquid state. So this is the example of actually redox reactions, so where oxidation reduction takes place. So this is example of redox reaction, right. So what happens here? Oxalic acid is reduced to this kind of CO2 and H2O, and here potassium permanganate, so that is oxidizing acid, so it will be reduced here plus 7 oxidation state, here plus 2 oxidation state. So potassium permanganate is reduced in these reactions and oxalic acid is oxidized into CO2, right. So in the presence of acid, so here this kind of actually potassium permanganate, it has pink color in the solution. So that is, you can simply say this is actually violet or pink color in the water medium. So before the reactions, the solutions remain pink, but after the solutions, now it becomes colorless, right. So this is colorless. So this is pink. So by observing the change in color of the reactions, we can actually assign the role of the catalyst. So here potassium permanganate act as a oxidizing agent. So right, oxidizing agent, right, as well as autocatalyst, right. So this is autocatalyst. It means it has a double tendency or dual nature, both. So it will be oxidizing agent as well as the catalyst. So this kind of redox reactions will proceeds through the process of autocatalysis. Now another example is the phase transfer catalysis. Phase transfer catalysis, in few days before, I have actually given you idea about the crown ethers and cryptanes in case of alkali metal chemistry. So here same, the phase transfer catalysis means a catalysis where phase transfer occurs, or you can simply say the reactant molecules may come from one phase to another phase through the presence of this kind of particular catalyst. So this is PTC, right? PTC, phase transfer catalyst. So here is most exciting examples, that is, you can simply say that is 18 crown 6. So this is actually macrocyclic ligands, that is crown ether, right? So once potassium fluoride, that is ionic compounds, so this is ionic compound, right? So in the presence of benzene, suppose this is your benzene liquid, this ionic compound in the, actually this is ionic compound, and this ionic compound is soluble in water, but it is insoluble in organic solvent. So benzene is a organic solvent, so that is non-polar solvent. So this polar compound or ionic compound is insoluble in benzene, right? So it cannot undergo in this particular phase, in the liquid phase of benzene. So it will remain as such in the solid state in the medium. But what happens if you add 18 crown 6 in the reaction medium, then this potassium is actually abstracted through the crown ether. So it forms, that is K 18 crown 6, that is actually +1, and here the fluoride plus F minus. What happens if you add this particular compound, so that is crown ether, then potassium plus, as a, actually this is salt, so it is K plus F minus, right? So K plus will enter into the host of this particular crown ether, right? Then it form a complex like structure, that is cationic complex, right? And the F minus will remain as such in the outer sphere of this particular cationic complex. Now this presence of this ion will ultimately dissolved in this particular benzene, and now the solution become pink, right? So here, what is the role of this actually compound, that is 18 crown 6? It will act as a phase transfer catalyst. Phase transfer catalyst, so this is in the solid state, right, in benzene, and it is insoluble in benzene, but in the presence of this compound, this potassium is actually enter into the host of this cyclic ligand, and it forms a complex like that. Now this 18 crown 6 has polar and non-polar both parts. So in the benzene, actually non-polar part, and in the outer periphery or hydrocarbon parts, they will interact to benzene, and it will solubilize the potassium fluoride. So then potassium fluoride undergo into the liquid state. So from solid state to liquid state actually obtained in the presence of 18 crown 6. So this is act as PTC, phase transfer catalyst. Another example is that, and here the fluoride anion that is poorly solvated with this particular kind of macrocyclic ligand, so it is highly reactive, right? So here the cation and anions both are present in the benzenes, and the solutions look like pink, and it is soluble, which look like that the compounds actually not pink actually. So this is another kind of, this is only, you can say simply not pink. So this is actually solubility behavior. Here another example that will clearly indicates, that is 18 crown 6, that is KMnO4. Now on the basis of the color we can actually try it. So KMnO4 is insoluble in benzene, right? But this is soluble in case of in the presence of 18 crown 6. So what happens now? K 18 crown 6, right, plus MnO4 minus, right? So what happens? Potassium permanganate is covalent ionic compound. It is soluble in water because of presence of potassium plus and permanganate ion, right? In case of benzene, it is not dissolved. Rather, it is remain as such in the solid phase in the reaction medium. But 18 crown 6 is added. What happens? Potassium plus is abstracted. So it forms a K 18 crown 6 like complex plus as a cationic charge overall, and then hence here cations and here anions both are present. So in this benzene, and now this actually solutions appears pink, right? But potassium permanganate when exist in benzene, they solutions does not appear pink, because all the potassium permanganate in the solid state they will be deposited in the bottom of the reaction medium, and clear solution will be on the top of this particular residue in the solutions. So but addition of this kind of PTC, actually phase transfer catalyst, the solutions actually look like pink and potassium permanganate is solubilized. So this is the actually role of phase transfer catalyst. So one phase actually enters into second another phase in the presence of a particular kind of reactions. So this is the actually beauty of catalyst, and the phenomena is called catalysis, right? So what happens? There are so many catalysts are present, and now research and innovations are performed to design the catalyst, because catalyst, as you know that catalyst are specific and selective, because a particular kind of reaction involves a particular kind of catalyst. It does not involve any kind of catalyst, because the nature of the products will be changed. So the catalysis and catalyst design is a very challenging task for a particular kind of reactions. Now what happens here is actually what is the use. So nowadays in the oil industry, right? So in the oil refinery industries, there is a most or you can simply say major use of catalyst for the hydrogenation of the unsaturated hydrocarbons to produce oil, right? In the pharmaceutical industries, so many products are actually obtained in the presence of, or you can simply say drugs are produced in the presence of catalyst. So catalyst has a very big role in the industry. Either you can simply say in the chemical industry also. In the chemical industry, so many chemicals are produced and they are launched in the market for various applications. So they are actually produced through the use of the particular kind of catalyst. Or you can simply say in the petrochemical industries, so many catalysts are used to actually to convert the hydrocarbons or decompose the hydrocarbons. Or you can simply say the catalysts are used in the vehicles or automobiles to as a catalytic converters, because in the petrol, or once the petrol is decomposed, so there is actually need to catalyst, so many actually emissions of the toxic gases are produced, like carbon monoxide, nitrogen oxide, or carbon dioxide, or any other toxic gases that is produced during the course of knocking up the petroleum products. So the petroleum products actually requires catalytic converters, right? So tetraethyl lead is the most important catalytic converter, so that is used in the automobiles or vehicles to stop the knocking up the petroleum fuels. So catalyst can be actually used to produce oil fuels or any chemical fuels for the variety of applications in the daily life, as well as in the industry or in the social life. So this is the actually beauty, and there are so many acid base catalysis also are important to understand the chemistry and catalysis. Now so depends on the nature and of the catalyst and the nature of the reactant molecules. So the reaction can be performed, and the product may be desired or maybe it is undesired. So the design of catalyst is important. So it should be selective, right? And it should be specific so that we can get desired products, because sometimes we have a reactions that is actually involved, so that have a specific role. So now what is the example? So that is actually here I have taken from the reference. So it happens like that. So some examples we have taken. The example look like that. Here, yes, we have a very good example. You can simply say, simply understand in the other page. So suppose we have ethanol, that is C2H5OH, right? So this is in liquid state. What happens in the presence of Al2O3, that is in solid state? It will be converted into C2H4 in the gaseous phase, and now H2O will be in gaseous phase, right? So this is what happens actually in the presence of this aluminum trioxide, the conversion of ethanol. The same conversion of ethanol C2H5OH in liquid state in the presence of copper solid. So it will form CH3CHO plus H2. This is your gaseous plus this is your H2 gas. So here you can actually see that this ethanol liquid solution, it can be decomposed into, that is C2H4 ethylene gas plus water in the presence of this catalyst, right? So same reactants are decomposed into different products here, that is acetaldehyde, right? CH3CHO plus this is hydrogen gas. So in both reactions products are different, right? But reactants are same. So why this happens? Here the catalyst is aluminum trioxide, here the catalyst is copper solid. So this reactions actually is specific because of the role of the catalyst is specific, to produce the desired product. Here aim is to produce acetaldehyde, right, from this alcohol. Here aim is to produce ethylene gas, that is organic compound, in the presence of this catalyst. So catalyst design is important, and it is selective, and it is specific to produce the desired products, right? So these are the examples actually used to enhance the rate of the reaction and to produce the products, either it is desired or undesired. So the main important thing is that that is activity of the catalyst. Activity of the catalyst, right? Activity of the catalyst means the number of active sites that involves the reactions, or actually it is used to create the collisions among reactant molecules so that they can actually produce the product. So this is the activity of the catalyst, right? So activity of catalyst depends on the turnover frequency, TOF, right? So turnover frequency means the amount of, right, actually this is defined as turnover frequency, that is actually defined as amount of, so this is defined as amount of substrate reacted, amount of substrate reacted, so upon amount of catalyst good time, amount of catalyst into time, right? So this is the turnover frequency. It is measured in a per unit time, right? So per unit time, the amount of substrate reacted divided by the amount of catalyst. So this is the actually equations that gives us idea about the activity of the catalyst. So activity means कि the catalyst must possess active sites or reactive sites, right? So if actually all the surface or all the sites of the catalyst are not responsible for the collisions or a particular kind of reactions, only few specific sites, or you can simply say reaction sites, are actually involving in a particular kind of collisions of the reactant molecules to form products. So the activity is important, right? And the productivity is related to the turnover number, TON, right? TON is nothing but only simply, you can simply say amount of substrate reacted divided by amount of catalyst only, right? Not time here. So if we remove this time from this equation, then it will be TON, right? So turnover numbers. So that will gives us idea about the productivity of the catalyst. So productivity of the catalyst means how many times it can be recycled. Yeah, you can simply say how many times or how many numbers it is actually used to particular kind of reactions to produce the products. So it will be turnover numbers. So one most important thing about the catalyst is actually promoters, catalytic promoters, motors, right? So catalytics promoters, actually promoters means, so it will promote the role of the catalyst, or you can simply say a substance which is used with catalyst to improve its activity, right? So if you want to increase the activity of the catalyst, then we have to add a foreign substance is called promoters, right? In case of Haber process during the synthesis of ammonium, so that is actually iron solid and molybdenum solid, right, is used. So iron solid, that is N2 plus 3S2, right? So here 2NH3, that is ammonia gas. Here iron solid act as a catalyst, and here molybdenum solid act as a catalytic promoter, right? So the sometimes promoters are required to enhance the activity of the catalyst which we are interested for the particular kind of reactions. So catalytic promoters, and sometimes inhibitors, and in the presence of foreign substance that will reduce the activity or retard the activity, they are called inhibitors, right? So during the process of production of sulfuric acid in the contact process, the platinum actually act as a solid catalyst. So in the presence of arsenic, so the activity of the actually catalyst is reduced or retarded, and accordingly the sulfuric acid is produced. So different type of actually catalyst and catalytic promoters, catalytic inhibitors actually playing a particular role in a particular kind of reactions, and we can get either desired product or undesired products. So it will solely depends on the nature of the catalyst, its mass, its composition, its structure, and its selectivity to a particular kind of reactions. So this is what actually the beautiful concept of the catalysis and the catalyst which are actually required to enhance the rate of a particular kind of reactions. So now I stop here. Actually the video is going to be too long. I hope the idea and the examples actually that will be much more beneficial and compatible to understand the chemistry of catalysis and the physical concept actually to help to understand the scenario of the catalyst and catalysis. So okay, thank you. If this video looks actually comfortable for your brain, then please don't understand to like, share and comments on this video. So that will actually promote me or activate me to improve the further videos. So I again thank to all of you. Please look and watch and listen this particular video on a particular topics. So thank you again.